Recording. Okay. So we're in the middle of proving this theorem due to Schreyer, right? And this theorem says that if we have a Grobner basis G1 up to Gm for a module in R to the n, then the basic syzygies, not only do they generate all the other syzygies, but they do so as a Grobner basis. So tau ij is a Grobner basis for the module of syzygies in R to the m with a certain order on R to the m. Remember that the point is that we already have an ordering in R to the n, which I kind of call this black ordering on black vectors. And using that, I defined a blue ordering on blue vectors that live in R to the m. Okay? And this was the rule to define the new order on R to the m. Okay? Yep.
What's that epsilon sub u? What's that mean?
Oh, epsilon u. These are basis vectors in R to the m.
Okay.
So it's a good point. Basis vectors of R to the n. Okay. So this is all with respect to a fixed choice of basis vectors. So last time I gave a proof of one case. So we did this when the G sub i's are monomials. Okay. And so I did this proof, but I want you to think about what this statement says in the case of monomials. Okay. Basically, what I'm claiming is that these basic syzygies generate all syzygies. Now, what does a syzygy on monomials look like? Well, every monomial is a single term, right? And so you have some polynomial times a single term plus some polynomial times a single term, etc., equal to 0. But the point is that because these guys are monomials, there's not going to be cancellation. And what we did is that we just looked in each degree. And in each degree, we just got a sum of monomials equal to 0. And we can understand the cancellation there. The point is basically that if you want to cancel a bunch of monomials, then you can only do it in the trivial way, because they're monomials. So you're not going to get any unexpected cancellation. So that was the idea for this case, when these guys are monomials. Okay? And now we need to do it for the other case, when we don't have monomials, when these GIs are anything. Okay? Okay, and so I'm going to do it like this. What do I need to do? I need to show that these tau ij's generate and are a Grobner basis for the module of syzygies. But we saw that being a Grobner basis is enough to generate. So I will only check that it's a Grobner basis. And as a consequence, I will know that they generate. So what I need to do, take a syzygy that looks like tau equals some summation of L of L epsilon L. So these guys are in F. Sorry, yeah. Well, these guys are polynomials, right? And so a syzygy looks like this. It's a blue vector. Okay. I guess you guys can see this, but students in Colombia can't see that I already did this. So let's wait for the camera to get here. So here, what I wrote is the same example that I had last time, right? So these were G1, G2, and G3. These were the basic syzygies tau 1, 2, tau 1, 3, tau 2, 3. And each one I think of as a column vector in my blue space Rn, but I also think of it as an equation. So this, for example, says that y cubed times G1 plus 0 times G2 plus minus x squared times G3 is equal to 0. So I can think of a syzygy as a column vector and as an equality. Okay. So this is the syzygy written as a column vector, but what it means is an equality. What it means is that when I take the epsilon L's and I switch them for GL's, then I get something equal to 0, as I said over there. What I'm doing here is applying this map phi that sends epsilon L to GL, and this guy is in the kernel, meaning that this guy goes to 0. Okay. Now, so what do I need? Well, I need to show that the initial term of tau is generated by the initial terms of these basic syzygies. Okay. So this guy is generated by the initial syzygies, the initial terms of the basic syzygies. Okay. That's what I need to show to be a Grosvenor basis. And so the first thing we should do is figure out what are these guys. We should understand them better. Okay. Now, I should remind you what tau ij is. So reminder that the way that we defined tau ij was like this. It was given by basically taking this mji epsilon I minus mij epsilon j. So remember, what we're thinking is that we're doing the Buchberger's idea, which is to take mjigi minus mijgj, and because that's a Grosvenor basis, I can write it as a summation of the other of the g's. Okay? And I do that, and I get some big summation that looks like this, and I use the notation f u I j epsilon u for u equals 1 to n. And mji is that term. Do you guys remember what mji is? Should I write it down? I guess we can write it down just to be sure. So I'll write it here. mji is what we need to cancel the. It's going to take me more space than this. It's what I need to cancel the leading term here, right? So I said that mji is equal to. There's two cases. So the first case is least common multiple of initial term of gi, comma, initial term of gj divided by initial term of gj times right. So this is in the case where if n of gi and n of gj involve the same EU and 0 otherwise. So that's what mji was. Okay? Yeah? I guess I should also say another piece of notation that I had last time, which is that what I'm writing there as E are the basis vectors over here. So here the EU are basis vectors of R to the U. Okay. So what's the relation between epsilons and g's? Actually, simply what it is that for each gi, I define an epsilon I. And so really, what I'm saying is G1 and Gm are some vectors of polynomials. And for each one of them, I'm just going to define a basis vector, epsilon 1, epsilon 2, up to epsilon m. And those basis vectors are going to span this space Rm. So that's the relationship. So you can think of each epsilon I as a kind of a formal placeholder for the polynomial, for the vector Gi. Yeah?
So each Gi vector has a set of basis vectors?
Yeah, so remember that, for example, in this example, we're starting in a computation that lives in R1. Okay? And so G1 is just a vector of length 1, a vector of length 1, a vector of length 1. Okay? And then we go to a computation in R3, which is where the syzygies take place. But it could be that the GIs are column vectors of polynomials. And if that's the case, then they're going to have components, and that's where I'm saying that a basis for those components is going to be E1, E2, up to En.
So we do have cases then where the GIs are vectors that are not just in R1?
Yeah. Yeah, so I am very interested in doing this not only for single polynomials GI, but for column vectors. Okay? And we'll see why in a second. Okay, so this was the definition of tau ij, and I claim that this guy is easy to understand, actually. The initial term of tau ij is just going to be this one. Tau ij is some big thing, and we need one of the terms to be the smallest one, the greatest one, and it's going to turn out to be just this one. Not this one, not these. It's going to always be the first one that we wrote down. Okay? So let me put this in a little box because this is important for our proof. So why is this true? Well, what we have to do is compare this monomial, and all of the monomials that appear here. How do we compare these things? According to that strange rule over there that tells me that if I want to compare a blue monomial with another blue monomial, what I do is basically I plug in the corresponding G here. I plug in the corresponding G here. I compute the polynomials MGU and GV and take initial terms. If an initial term wins, then this guy wins. And if there's a tie in the initial terms, then you just go by the subindex. So what happens when I do this? Well, what's going to happen is that what's the initial term of this guy? Sorry, the initial term of MJI GI is what I need to compute for this one. For this one, I need to compute the initial term of MIJ GJ. And for each one of these guys, each one of these things is going to be some monomial. And if M lives in here, then I need to, for each one of those M's, I have to compute the initial term of MGU. Okay? Now the thing is that this expression was the product of long division. And what you should remember is that long division works so that we cancel the biggest term here with the biggest term here, and all of these terms are smaller. And so what that means is that these two initial terms are equal to each other, and they're bigger than everything that appears in this guy. And so we're looking for the initial term in this expression, and we only have two candidates for it. This guy and this guy. Okay? And this guy have the same initial term precisely by the definition of Mij and Mji. We chose Mij and Mji so that we would have a cancellation in the initial terms. So that's where this definition comes in. So that's why I have this equality, and these guys are all smaller. Question?
So to get rid of those two, how do we figure out which GI and EJ we had to get rid of? How do we know what one of those EUs that was our biggest thing we wanted to cancel out?
Well, that's a good point, because
It sounds like we're assuming we know the initial term of tau and that we want to cancel it, and then you're saying we want to find it. But
sorry, can you repeat your question?
it seems as though we know which one we want to cancel, right? We want to cancel the biggest one of these. When we're doing that, when we're doing the lowest common multiple and then the JIs and all that.
So what I was saying is that if you take the epsilons and make them G's, okay, because this is a syzygy. So I can think of it as this vector, Or I can think of it as an equality that if I put g's here, I get equal to 0. So in that equality, I do know the orders, okay, because that's in the initial ring, in the initial module, okay? And that's where I'm saying that it's over there that I compute initial terms. And over there, I do know what the order is. And what I'm trying to do is infer from that what the initial term is in my new module. Okay? And I'm claiming that this is what I know how to do now. And this is the reason. Because the candidates are these guys and these guys. Sorry, it's this guy and this guy. None of these guys can be the biggest. And when you have a tie between this and this, you're just supposed to choose the smaller index. Okay? So because I have a tie here, I'm supposed to choose the smaller index, which in this case is I, because I index the tau ij so that I is less than j. So that's the first claim, is that I do know what these initial terms are. These initial terms are just mji epsilon I. Okay? And then I'm going to say this. I take my syzygy tau, which represents an equality. And this equality looks like this. Well, let me write it like this. So I have my syzygy tau. Okay? Now, the statement that I'm after is that I need the initial term of tau to be generated by these guys. Okay, but I don't know what the initial term of tau is, and so I want to give it a name. So the initial term of tau is going to be just the biggest possible thing that we see here. Okay? Now, the initial term of tau is going to come from one of these guys, between 1 and m. Okay? So what I'm going to do is that first I'm going to, for each L, I'm going to decide what's the initial term. Okay? And it's going to be something, some monomial times epsilon L. Right? So now I know for each one of these guys what's the biggest term. Okay? And now for tau, basically the initial term of tau is going to have to be one of these initial terms. So the initial term of tau is going to have to be one of these guys, and let's just say that it's the ith one. One thing you should realize is that because these epsilon L's are basis vectors, you don't have any cancellation in this equation. Right? F1 epsilon 1 occurs in the first variable, F2 epsilon 2 occurs in the second variable, etc. So there's absolutely no cancellation here. So if you want the biggest term here, you just have to search for the biggest term in the sum ends, and you know that that guy's not going to get cancelled. Okay? So I define this and this, where n sub L is some monomial in my ring. Okay? And this is one of the indices I. Okay? So now I'm going to say this. I take this syzygy that looks like this. Okay? So this is some equation, something equal to 0. And I'm going to say, look at the initial term that appears here. Okay? In other words, take the terms in this equation of largest degree. Now, largest monomial. Okay? Last time I confused someone by switching monomial and degree. Take the terms involving the largest monomial. Okay? Now, the point is that what are the largest monomials here? Well, we decided that the largest monomial for each one of these guys was going to be NL epsilon L. And how do we decide that? We decide that by plugging in the epsilons into G's. Okay, so if we know what the biggest term is in terms of the epsilons, then we know that the largest monomial that appears here, so this involves the monomial it has to be this monomial. Ni epsilon I is the largest degree term in the syzygy, and so this is going to be the largest degree that exists in this equation. Sorry, Ni times the initial term of Gi. This is the largest possible thing that can occur here, and it must occur several times because it gets cancelled, right? I mean, if I look in this sum at all the terms of this degree involving this monomial, they have to cancel out. Okay? And so I take those guys and consider only those. Which ones are those? Well, they're the ones that look like this. NL, initial term of GL, equal to 0, where these are the L, these are only some of the L's. These are the L's such that NL, initial term of GL, equals NI, initial term of GI. So I take this equation, I look at the very largest degree, and I get some other equation that looks like this. Okay? Now, there's one thing you should notice. So this is the definition of S, right? S is L such that this occurs. Okay? Now, there's one thing that you should realize, which is that Ni epsilon I is bigger than NL epsilon L by this decision, right? That this guy is going to be the very largest one, so this guy has to be larger than these guys. Okay? So if these guys are, if Ni times the initial term of Gi equals NL times the initial term of GL, that means that the first criterion of comparison didn't work. It must have been the second comparison that I used, meaning that I must have been less than L here. So this implies that I is less than L for L in this set. Okay? And we will need this in a second also. Now, what is it that I'm trying to do? Well, the point is that I wanted to start with a normal syzygy of these complicated polynomials. They're GIs, they have several terms. And what I did is that by looking at the very highest degree, I got a different syzygy. And this is the monomial syzygy, because these guys are monomials, and these guys are monomials. Okay? And so the point is that I started with my complicated setting, and I ended up in a setting where I have syzygies and monomials, and I can use the first case that I proved. Okay? So, in other words, what I'm saying is that this thing is a syzygy of these initial terms. Okay. Let me call this tau prime. Okay. So I started with my normal syzygy tau, and I got a new syzygy that's a monomial type syzygy. Now, because it's monomial, that means that I can apply this result for monomials because we already proved it. Okay? So by the monomial case, this syzygy tau prime has to be a combination of the basic syzygies of these monomials. Okay. So it is a combination, right, like this. Tau prime is a combination of the basic syzygies of this new set G prime. Okay. In other words, tau prime I can write as some combination of the basic syzygies, which maybe I'll call tau prime. So basic syzygies, let's call them tau prime sub ij of G prime. Okay. So I get something that looks like this. Now the thing is that if you look at this for a second, you'll see that my definition of tau ij is going to be the same as the one for tau prime ij, because these coefficients that I paid attention to always refer to the initial terms. Okay? So that means that when you plug into what tau prime ij is, you're going to get exactly the same definition here. It's going to look like this. Okay. And this is for 1 less than or equal to I less than or equal to j less than or equal to, well, I mean, this is for I and j and s, basically. I'm realizing that I made a bad choice of notation because I has a meaning for us. I was fixed here. So let me, instead of using ij, I'm going to switch to j and k. So every time I see ij, I'm going to switch to jk. Okay. Now here, I'm almost done because you see the point is, I want to look at the initial term that appears here. Okay. What's the coefficient of epsilon I here in this equation? Well, you see, in tau prime, the coefficient of epsilon I is going to be ni, right? Ni epsilon I. Okay. And what's the coefficient of epsilon I going to be here? Well, the thing is that if you look at what tau jk is, tau jk looks like this. M kj epsilon j minus m jk epsilon k. Okay? So if you want to produce an epsilon I, then either j has to be I or k has to be I. But furthermore, j and k are in S. And what I said here is that everything that appears in S has to be I or greater. Okay? So that means that if I is going to appear as the role of j or k, it has to appear as the role of j because it has to be the smaller one. Okay? So in other words, when I look at the contribution of epsilon i's that I have here, it's going to look like this. For all the k's in S, I'm going to get the term mk, well, I get aik is the coefficient, and then mki epsilon I is the contribution from here. Okay. And if you look at this, we're done. Why are we done? Because we needed the initial term of tau to be generated by the initial terms of the tau ij's. The initial term of tau is n I epsilon I. And the initial term of tau ij is mj I epsilon I, which is basically the same thing as here, but instead of ki put a j. So basically this proves what I needed. Okay. So that puts an end to this proof. Okay. I know it's a confusing proof. You should stare at it and look at it carefully. But that's it. So that's how you prove Schreyer's theorem. Okay. Any concrete questions other than what just happened? It's a bit of a tricky proof, but if you look at this, I never really said, oh, here's something clever I'm going to do. I just kind of worked and I got it. And that's how the proof is, and you should look at it and see what this is. But more important than the proof is the theorem, and the theorem is what I want to be very clear to you. Okay? So again, the theorem is, if you have a Grosvenor basis, then for free you get a Grosvenor basis for the syzygies. Okay? The basic syzygies are a Grosvenor basis for all the syzygies. And the basic syzygies we saw are very easy to compute. Maybe I'll write this in a box and erase the proof so that I emphasize what I think is most important. So, in words, if you have a Grosvenor basis for a module, then you have a Grosvenor basis for its syzygies. Now remember that there are many reasons why having Grosvenor basis is very useful, and the main one is that it allows us to compute very easily. Okay. So if you have a Grosvenor basis for the syzygies, that means that you can perform computations on syzygies very easy. So this is this, and there's some technicalities involved, but that's the philosophy of this theorem. Okay. So I think maybe what I would like to do now is an example of all of this, because I'd like to emphasize that this statement is actually pretty important for the next thing that we're going to do. The proof is not so important for what we are going to do, but the statement is. So let's do a big example of this. And so by the way, hopefully you got my email that the next homework is posted. And you should pay special attention to this example, because I'm asking you to do something very similar to this in one of the homework problems. So example, let's say that I'm in the ring of polynomials in 3 variables, and I'm going to consider the following module is going to be the ring quotient, the ideal generated by x, y, and z. Okay. I want to perform some computations here. So here's the maybe step 0. I mean, what's the story? How should you think about the computation that I'm about to do? Again, the thing that you should think is that when you compare this to linear algebra is very easy, and here this is harder. Okay? I told you that a module is kind of like a vector space over the ring. So we kind of want to understand this as a vector space. Now, an easy way to understand an ordinary vector space is you just choose your bases, and then it's just combinations of those things. Okay? And so I want to start by doing something similar, which is saying at least, okay, how can I generate everything that lives here? Okay. So that's my question to you. How can you generate M? Can you give me a set of generators? Can you tell me an element that lives in here? So 0 lives in there. And 0 is not generally what we want to use to generate other things, right? And 1 is something that lives in there, and we can generate things with 1. So 1, what do we mean by 1? We mean the coset of 1 when we quotient out by this ideal. So 1 means 1 plus this ideal. Okay? So that's an element. What's another element? So 0 is another element, right? But we're not going to use it to generate. Any element of f. But if you think about it, any element of f is generated by 1. It's 1 times that element. Is there anything else? No, right? Because the thing is that modulo this ideal, you can reduce x's, you can reduce y's, and you can reduce z's. So any polynomial in this ideal, you can just reduce it to be the constant coefficient and just throw out all the x's, all the y's, all the z's. So actually, this guy by itself generates. So let's call it 1. Let's call it 1 bar to be a little bit careful. So 1 bar means the polynomials with leading coefficient 1, with independent coefficient 1. Okay? Now, I think you will be very disappointed if you ask me to explain this to you, and I tell you it's the module generated by 1. Because if I asked you to think about the module generated by 1, you probably are going to think of the ring. The ring is also generated by 1. Right? So this is not a lot of information because, okay, 1 generates it, but there's kind of not enough information there. So what we need to do is say, okay, well, that's it. Those are generators, but what are the relations? And that's what happens in modules that doesn't happen in vector spaces. So what are the relations here? Relation is what? Syzygy, right? That's the word. So can you tell me some syzygies? Relation satisfied by all 1 elements of this generating set. So you're supposed to give me a linear combination of things, a linear combination of 1s that is equal to 0. Okay? So 1 minus 1 is it's a syzygy, but it's kind of the trivial syzygy, right? Because I mean it is a syzygy, right? So 1 times 1 bar minus 1 times 1 bar is equal to 0. The reason that this is not too interesting is because it happens in any module and for anything here. But can you tell me an interesting syzygy that this guy has that the polynomial ring doesn't have? Remember, you're allowed to multiply by polynomials. Right? So you need linear combinations, but the coefficients are polynomials. So that means, for example, if you take this element 1, you can multiply it by anything and see if you get a relation. So for example, if you multiply it by x, you get 0. And that's something that is true in this module, but it's not true in the free module on one generator. Okay, so that really is a non-trivial syzygy. And okay, well, if I give you this one, you can probably think of 2 more. Y times 1 equals 0, z times 1 equals 0. And you can probably think of other ones, but the point is that the other ones are generated by these. The point is that what are the possible syzygies? Any polynomial whose independent coefficient is 0 multiplied by 1 is going to be 0. For example, x plus y times 1 is 0, x squared times 1 is 0. But the point is that any of those guys are generated by these guys. Okay? From this, you can deduce that x squared times 1 is equal to 0. From this one and this one, you can deduce that x plus y times 1 is equal to 0. So these generate, basically. These are the basics. These are syzygies are enough to generate all the other ones. Okay? And so, let me go to step 1 then, which is that the syzygies are generated by 3 syzygies: x, y, and z. Let's say that this is the syzygy module. So the syzygy module is generated by x, y, and z. Okay? Where does the syzygy module live? Well, syzygy module is a module of syzygies in R to the m, where m is what you started with. M is 1, and so this is something that lives in R to the 1. Okay? R to the 1 is just polynomials. So these are 3 polynomials, and they generate. So, okay, so that's fine, because that means that now we understand the generator, and we understand the relations that it satisfies. Okay? But then, why stop there? Now we know that the point is, okay, well, here we have some syzygies, but now are there relations between them? Okay, because the syzygy module is not a vector space, so it's not enough to tell you what is generated by. I should tell you what relations hold in the syzygy module. Okay? So what are the syzygies of the syzygies, in other words? Syzygies of the syzygies. So can you tell me, let's call them B1, B2, and B3. So what are some linear relations between B1, B2, and B3? Well, to start with, we have the basic ones, right? Take the leading terms. Leading term, leading term, leading term. That's kind of boring. Okay? And then just compute those things that Bookberger tells us to compute. Y times, so what's S of B1, B2? S of B1, B2 is yx minus xy. Okay, so y times B1 minus x times B2 is equal to 0. This is the basic syzygy S1, 2. Then we also have S1, 3, which is zB1 minus xb3 equals 0. And then the syzygy 2, 3 is zb2 minus yb3 equals 0. A consequence of this computation is that because the 3 basic syzygies give me 0, that means that this is a Grosvenor basis for the syzygies. And as a consequence, these 3 things that I wrote here are a Grosvenor basis for the syzygies of the syzygies. Okay, so now let me write the syzygies of the syzygies. So, syzygies, maybe we can go, let's see, how much longer do I have to go here? Syzygies of the syzygies is generated by, now these guys, okay? But now it gets a little bit more interesting, because where do these guys live? Well, they live in R to the number of generators in the previous step. Here I have 3 generators, so these guys are going to live in R3. And what are they? Well, here they are. Y minus x, 0. Then z, 0 minus x. And then 0, z minus y. Okay? So those are the syzygies of the syzygies. These guys generate. But again, we can't be satisfied there. We need to know the relations on these guys too. And so this is no moment to stop. We have to keep going. Syzygies of syzygies of syzygies. So how do I do that? Well, The good thing is that this is easy because I have a Grobner basis by Schreyer's theorem. You have to see what the initial terms are. The initial terms in this case are this one, and this one. And then I'm going to compute the syzygies of the syzygies of the syzygies. And I know that I just need to compute the basic ones. So if I call this C1, C2, and C3, then I need to compute these pairwise syzygies. So what is S of C1, comma C2? It's whatever makes these guys cancel out. This Y and this Z. I accomplish that by taking Z C1 minus Y C2. So Z C1 minus Y C2. And then I express that in terms of C1, C2, and C3. But if you see, Z C1 minus Y C2 is 0. So I can just stop there. Okay. So that's the first syzygy. What's the second syzygy? It's whatever cancels this Y with this Z. But this is where you start to see some of the technicalities in the previous proof. There's no way to cancel this Y with this Z because they're in different components. And so that's why in this definition that I had here, I had two cases for S of something something. Either it's something interesting or it's 0. So here you see that happening, that S of C1 and C3 is 0, so there's no syzygy there. 0 equals 0. And S of C2, C3 also is nothing because you can't cancel this guy and this guy. 0 equals 0. Okay? So the syzygies of the syzygies of the syzygies are generated by this one. How many coordinates should I give it? How many entries does this have? It looks like there's only 2, but remember that this is supposed to live in R to the number of previous generators that I had. Here I had generators C1, C2, and C3. Okay? And so I need to say, what's the coefficient of C1, of C2, of C3? So I have a single syzygy that generates. Okay, so then syzygies of syzygies of syzygies of syzygies. Okay. What do you think I'll be able to finish by the time class is over? Well, this is the good news. Look at the syzygies that we have. We just have D1. Okay. Now, again, by this theory, I had a Grobner basis here, which means that I have a Grobner basis here, which means that I have a Grobner basis here. This is a Grobner basis. Its initial term is this one. Because this is a Grobner basis, the syzygies are generated by the basic syzygies. And what are the basic syzygies? You don't have any because for a basic syzygy you need 2 terms. But there are no basic syzygies. And if you don't have basic syzygies, that means that you don't have syzygies. And so finally, we're done because finally we reach a point where there aren't any further relations, and now this looks like a vector space. Okay? So finally, this is nothing. Okay? No syzygies. So finally, I can stop. Okay? Finally, I can stop. And finally, I can tell you the whole story of how I can generate this module M. And this you should think of as the equivalent of specifying a basis in vector spaces. That was very easy. Here, it takes more work. You have to do this, and this, and this, and this, and this, until you're done, if you're done. Okay, but here we maybe got lucky and it's finished, but we didn't know if we had to be here until 5 o'clock or until tomorrow or when, right? Or it could be that this never ends. Right? So this is the kind of computation that we need to know how to do. And this is what Grobner basis is going to allow us to do. Okay. Now, I need to make a definition for you, so you can see it, and so you can start basking in how wonderful it is and be ready for it next time. Okay. I want to summarize I want to summarize this story like this. Okay? Have you guys seen diagrams like this before? Is it familiar? Maybe to some of you. So what's this? Well, this is a bunch of modules, right? And this is not what you're used to seeing if you haven't seen it before, because generally we know what an arrow means, right? It means map this module to this module. Now, when we have a whole thing like this, then you should just think that these are a bunch of modules and a bunch of maps between them. So what do I have here? Well, these numbers 1, 3, 3, and 1 are the things that appear here. 1, 3, 3, and, well, here this was 0 in R1, right? Okay. And so this whole story, it's a pain to have to write it like this, so we write it like this. Now, what are these homomorphisms? Well, this one is easy because from here to here, we're just taking modulo. So this is just taking modulo the ideal. Okay. Now from R cubed to R1, we're considering this map. Let me color code this. So here, we're considering multiplication by this matrix. Here we're considering multiplication by this matrix. Here we're considering multiplication by this matrix. And here, well, there's not a lot of options on how to map a 0 module into something because you just map 0 to 0. Now, so these are homomorphisms, okay? Now you should realize that for each one of these guys I chose a basis, right? So this guy has basis A1, so maybe this guy, basis A1, B1, B2, B3, C1, C2, C3, and D1. So these are the bases, and these are the transition matrices that tell you how to map a module to the next module. Okay? There's one thing that you should realize, and that's the most important thing, which is that no matter where you look, the kernel of this map is going to be the image of this map. Okay? So if the kernel of this guy is the image of this guy, we call this an exact sequence, and we call something like this a free resolution of the module. Okay? So this is not something you're supposed to get right away, but we'll practice with this definition. So this is exact if at each step you have that the kernel of G lives in M, and the image of F lives in M. So this is exact if the kernel of G is equal to the image of F. And a free resolution of M is an exact sequence that ends with M and has